discuss on how we can numerical methods of solving a second order differential equations. Okay, so for that we introduce numerical methods. Numerical methods are approximate solutions to differential equations by taking discrete steps using techniques like these are some techniques which is called Euler's methods, Hans method, and Runge-Kutta method of ordinary differential equations. And there is another method is called a finite element method of partial differential equations. So partial differential equations we use finite element method, which will be discussed later. These methods are crucial when analytical solutions are difficult or impossible to find, relying on initial conditions and small step size of to iteratively calculate numerics. Which means these are very useful when the differential equations are become very complicated. It cannot be solved analytically. You can use one of these methods. The few methods are called Euler's method. This is one of the simplest numerical method. And another is called Runge-Kutta method. Runge-Kutta method is little bit advanced. Then Euler method can be improved. The method is called improved Euler method, which is called Hans method. Okay, we will discuss Euler method and Runge-Kutta method in detail. And okay, Euler method. What is Euler method? Euler method is a simple first order numerical technique. So this is particularly useful to solve the first order equations, to approximate solutions of first order differential equations by using tangent line approximation to step through the solution curve. It relies on the idea of moving along the tangent line of a curve over a small straight line segment to estimate next point to the solution curve. This process is repeated to build an approximate solution. Okay, so we will discuss on how this method. The first order ODE. So the equation should be in this form: y dash x, which means dy by dx. It should be a function. We can maybe any function of x and y, maybe x plus y or x plus 3y, etc. We should give any initial conditions. One condition, it will state what is if x0 is 1, then y0 is what. The Euler method uses to find the iterative formula to find the next point yn plus 1, xn plus 1 and yn plus 1. Okay, so we will use these initial conditions to estimate the next position. So using this equation, the next step of x should be xn plus 1. That should be xn plus h. Then yn plus 1 is, this is Euler formula, which is giving yn plus h into f of x and yn, where h is the step size, the step in which you are moving the x-axis. Then xn and yn are coordinates of the current point. Okay, then f of x and yn, function of x and y is a derivative, is evaluated at the current point. Okay, we will do, this is an Euler method of algorithm. We will define the function of xy, which should be dy by dx should be is equal to f of xy. We have to find that what is the function. Then input x0 and y0, which is the initial conditions. I input h and what is the step size you needed and n, and we have to do the iterations for the Euler method. So this is iteration. So you will increment this y and x by each step. Then you should print the required output. Okay, so we will do one simple problem, which is apply Euler techniques to order differential equation to this equation: dy by dx is equal to x plus y, where y of 0 is equal to 1. This is the initial condition, which means that if I put x is equal to 0, I should get a y is equal to 1. Okay, and also it's given that using the increment of size, h is equal to 0.2 and h is equal to 0.1. Okay, the step size can be, first you can estimate 1.2 and h is equal to 0.1. Okay, so how to solve it? So for solving this, we can follow the algorithm. We have the function dy by dx is equal to x plus y. Okay, so what you do, you can estimate first h is equal to 0.2 here. Then the next step is you have to find the next point. Okay, what you're doing, you have to substitute the equation previously discussed, ya plus 1 is equal to ya plus h into f of x0 y0. So our next point y1 should be what? y1 is equal to y0 plus, here h is equal to 0.2 into f of x0 y0. So I can substitute this value, then y0 plus h into f of x0 y0. Y0 is now it's 1, then my h is 0.2, and f of x0 y0 is x plus y. Here my x is x0 is 0, then y is 1. Okay, I've substituted this one, I will get 1 plus 0.2 into 1, it should be equal to 1.2. Now the initial point should be 1.2. I have to do the next iteration for 0.4. That can be continued to up to 1. So I can make a table where xn is can be incremented by 0, 0.2, 0.4, 0.6, 0.8, 1. I can estimate yn from this one. Starting from 1, next is 1.2, 1.4, that can be calculated. Then there should be an exact value. If I solve this equation exactly, this should be the value, which means that analytically I can solve it and give the values. I will get the exact value. So there should be some difference. All the numerical solutions have some errors. Here the errors, you can look at this is the percentage of error you can calculate. This should be very large if you are going for up to steps. So if you're increasing the steps, you are getting a very large error for the Euler method. So this is one of the disadvantages of Euler method. Okay, so similarly I can also calculate with the smaller steps. Okay, if I do the smaller steps, h is equal to 0.1, I get the results like this. Okay, so if you look at this one, it involves much calculations. I am not showing the calculations, but this is important that if you are storing a lower steps, you are getting an error of 7.2 only. Last you get on 13.4. So one way to decrease your error in Euler method is to decrease your step size to a minimum value. Okay. Anyway, your error is also very large. Okay, so how we get an exact solutions for this one? So we can also solve this by analytical solutions. This also involves a lot more steps. I will not go to detail, but I just say how we can solve it analytically. So this is my equation: y dash minus y is equal to x, or y dash is equal to x plus y. I can use this. This is solved by an integrating factor method. I can find the integrating factor. I is equal to e raised to minus x. Then I multiply the entire equation by integrating factor. E raised to minus into y dash minus y is equal to x into e raised to minus x. So I can rearrange to this, getting this one. Now what you do is I want to integrate these equations to get the with respect to x. So I will get this one, and finally I have to use the integrating formula like u dv is equal to uv minus v dv. Then I can get solved like the equation like this, and this also involves some more steps. Then I finally use this initial conditions, etc. Then I will get an expression like y of 1 is equal to minus 2 plus 2e. Then I put the value, then I get a 2e minus 2. At x is equal to 1, my value is 2e minus 2. I can substitute the value of e, which is about 2.7. I will get a value of 3.436 at 1. If you are looking at this is the same value, 3.431. For each of this value you can find these exact solutions. The problem is that you cannot find the exact solutions for more complicated equations. Since this is a simple equation, I can find the exact solution and make a comparison. But complicated equations, we have to use the numerical methods. Okay, then I said that Euler method is not very error free. We have to look at for another method which is called Runge-Kutta method. The Runge-Kutta method is widely used and reliable numerical technique for approximating the solutions of modern differential equations, ODEs. particularly for initial value problems. It's more accurate than simpler methods like a Euler method. So this is equations. I will not go to the detail. What you have to do is, this is the equations, and then you have to do the iterations. If you know x0 and y0, you have to do y1 is equal to y0 plus 1 by 6 into m1 plus 2 m2 plus 2 m3 plus m4. Then you have to find the each m1. The m1 is the step size h into f of x0 y0. x0 y0 you can get it from the initial conditions. Then m2 is the point where h into f of x0 plus h by 2 y0 plus m1 by 2. Then you need to find the m3, that is h into f of x0 plus h by 2 y0 plus m2 by 2. You have to use the m2 here to estimate the m3. Then finally have m4, which is h into f of x0 plus h y0 plus m3. Okay, you can directly use this equation to get the estimation to this differential equation. Okay, we also do the same problem in Euler equations. We can also try for the Runge-Kutta method, whether it is giving a better results. Okay, applying a Runge-Kutta method for the differential equations y dash plus x plus y. Remember that this is same equations we have solved for the Euler method. y0 is equal to 1. Then take h is equal to 1. Last time we put a smaller h is equal to 0.2. We directly try with the h is equal to 1. What will happen? Okay, so there is only one single step is involved. Therefore, I can substitute this value. I can find the m1. m1 is h into f of x0 y0. That is, my h is 1. f of x0 y0, I can x is equal to 0 plus 1. I should get 1. And m2 is h into f of x0 plus h by 2 plus y0 plus m1 by 2. H into h is again 1. I can substitute this value. I should get a 2. This 2 I can use in the next step and find the m3. Then finally I have to find m4. I get a 4.5. Then I substitute all these values in the equation y1, which is y0 plus 1 by 6 into m1 plus 2m2. I can substitute all these values into here. I will get an estimation of 3.417. Okay, so if you look at this solution, you can say that this is much closer to the exact solution than the Euler solutions, which have a lower steps. Okay, that means that the Runge-Kutta method is more preferable than Euler method because it gives better results compared to Euler method. Okay, you can make a comparison of Euler method where I have made the Euler method result for h is equal to 0.2, a smaller step size. I get a 13.4% of error from the Euler method. But in the case of Runge-Kutta method, if I try with the h is equal to 0.2, so here I have to deal with the 0.2 steps from the comparisons. I can make all the tables. Then I can find that the error is very much less. It's a 0.00179, and it is exactly almost nearby the exact solution, 3.43650.